Hey everybody, I'm back. We just finished talking about the unit circle and how to get all those values from the unit circle. But it turns out that you can actually expand the definitions of trig functions beyond the unit circle. And so these are actually what the definitions of trig functions are. The trig function sine of theta gives me the ratio of the y-coordinate on that circle with the radius of that circle, divided by the radius of that circle. When the radius is 1, as is the case in the unit circle, then you can see that sine of theta is just equal to y, which is what we've been talking about. But if the radius is not 1, then we need to take this into consideration. Now, if the radius isn't given, but they give us a point on the unit circle, we can use this formula that's right here. This is just the Pythagorean theorem, or the distance formula, if you really want to think about it. If we think about a circle, and we think about it not being a unit circle, okay, the radius, right, of this circle, if I wanted to find the length of this right here, if I know the x and y coordinate of this point, then x squared plus y squared equals r squared, right? I mean, technically they're not squared here. This is just x, y, and r. But x squared plus y squared equals r squared, and so r is equal to the square root of x squared plus y squared. So that's where this comes from. But the definitions otherwise are exactly the same as they were. It's the y-coordinate, the x-coordinate, the ratio of y over x. Tangent doesn't change. Cotangent doesn't change if the radius is something other than 1. The reason for that is if we're talking about tan of theta being y over r divided by x over r, then the radii cancel anyway, so the radius cancels and we just get y over x again. So that's why these two definitions didn't change. And you can see that this is still the reciprocal value over here. So now we're going to just talk about the quadrant in which an angle must lie, and we have to think about what we talked about on the first day of class. We talked about the coordinate plane, and we talked about the different quadrants. So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. And if we think about a coordinate that's in any of these quadrants, in the first quadrant, the x and y coordinates are both positive. But in the second quadrant, the x coordinate is negative and the y coordinate is positive. And in the third quadrant, the x and the y are both negative. And in the fourth quadrant, the x coordinate is positive, but the y coordinate is negative. And knowing which coordinate is positive or negative is going to tell you whether your trig function should be positive or negative when you plug in an angle, because remember, cosine is just the x-coordinate of all of the points on a circle. And so if we're in the second quadrant, then cosine of an angle that brings me into this quadrant should be negative because the x-coordinate is negative. And if we're in the third quadrant, then cosine should still be negative, but sine should also be negative. And since tangent is the ratio of the sine and the cosine, if they're both negative, then tangent is positive. And so looking at what this problem is actually saying, if tangent's positive but cosine is negative, which quadrant is my angle in? It has to be the third quadrant. I don't know exactly where. It could be anywhere between here and here. But the angle starts here. It always starts on the x-axis and goes around. So any angle that would land me in the third quadrant is going to have a tangent that is positive because y over x, a negative value over a negative value, is still positive, but cosine is negative, telling me that the x-coordinate must be negative, and so it can't be the first quadrant. The first quadrant, tangent is also greater than 0 here. but cosine is also greater than 0. And so it has to be the third quadrant. So the answer to this question is third quadrant. Okay, so in the next video we're gonna take this example and expand upon it a little bit. We're getting pretty close to the end, so